Hello, everyone. It's wonderful to be here today. When we discovered about 2.5 years ago that we were facing an enormous challenge in our world, we put together a team, a multidisciplinary team, to address the issues that we're going to talk about today, and some of the issues that you talk about all the time as you develop materials for the built environment. So the challenge for all of us was that we were living in a situation where things were unknown. We knew we had a threat. We knew the threat was biological. We could bring all of our biologists and chemists and risk assessors to bear on that. What we didn't know about is how some of the chemicals that we needed to use, some of the techniques we needed to use, how that would affect the interior environment. And so we worked with designers, we worked with architects, we worked with engineers, we worked with mechanical engineers to understand not just what we see in the environment, but what we don't see. The air, how the air moves, how it's resupplied through HVAC systems, which is heating, ventilation, air conditioning systems, and ultimately how all of the things that we had to do to develop this bouquet of solutions to the problem we were facing would affect that interior environment. So a changing world? Yes. Fortunately, we had some experience with SARS-CoV-1 and with MERS. They're similar types of coronaviruses. And we thought at the outset that this changing world was going to be very temporary. Maybe in a matter of weeks or months, the issue would be solved. As we know, that didn't happen. And so we had to persist in developing new ways to address how the world was changing and how people were changing in that world. So we're going to talk about this from three tunnels. One is the science as associated with pathogens. Pathogens are things that hurt you. They cause a pathological effect. They're not something that you want to have inside you. They're not something you want to deal with from a health perspective. Fortunately, you have a system within your body, which is the second tunnel you see here, called your immune system. And if things work right, your immune system protects you. If things don't work right, it actually can work against you. We're going to talk about those interplays between pathogens and immune systems at the beginning. And then lastly, we're going to talk about going forward. Not that we think this pandemic is going to last forever, but we know now we have to be prepared. We have to make some changes in how we view our interior environment. And that's the last thing we're going to talk about today, is those proactive changes that can be made. So science and pathogens, here we go. What you see here are microorganisms, which is just a fancy way of saying small organisms. Not all of these all the time are pathogens, but some of them can be. I'm going to talk about the ones first that are most like you. Their cellular structure is most like yours, and that's fungus. Fungus is in the group fungi. We also call these molds, yeasts, mushrooms, and they have a unique lifespan because they live in two different ways in our world. Part of the time they're living as vegetative structures. They sort of look like plants. So that's why they call them vegetative, like a vegetable. But part of the time they live as spores, and those spores contain their genetic material. If the spores are covered with a hard outer casing, they can actually live in the environment for quite a long time, and they can live in a wide temperature range. And as they move through the environment, they can sort of set up shop in drywall, on the side of the bathtub, and in you. They can enter your lungs. They can enter your digestive tract. They can affect your health. And so some of the things we're familiar with have to do with nail infections that can occur, skin infections, but also the lung and the bloodstream can be involved with these infections caused by fungi. The next one is bacteria. Bacteria are like the prototypes for what we are now. They're a cellular structure. They have some of the same dynamics as your cells, but their genetic material is not encased in a nucleus. Why all of this is important is because with bacteria, we have a chance to essentially destroy bacteria through desiccation, through drying events. Sometimes we don't have to rely on chemicals to do that. Other times we do. The alcohol that you put on your hands mainly disinfects against bacteria because it causes them to dry out, shrink, and no longer be capable of being a life form. Unfortunately, we have some types of bacteria that don't follow that recipe. They also form a hard outer casing, and that hard outer casing allows them to live longer and to be less prone to desiccation. One of the things you could remember if you were around when 9/11 happened is we had an instance in the United States where we dealt with anthrax. Anthrax is an example of one of those types of bacteria. It can live a long time in the environment. It doesn't take a lot of moisture. And so to destroy it, we have to essentially destroy that outer casing. These two life forms, fungi and bacteria, can live independently, but the next one cannot. The next one, viruses, is a true parasite. It only can make other viruses if it takes over another cell. Can it live in bacteria? Yes. Can it live in fungi? Yes. Can it live in you? Yes. And how it lives is it essentially sticks on to the cell and then injects its genetic material into that cell, takes over the cell and forces it essentially to make more virus particles. Now, we're familiar with the flu and colds and measles and chickenpox and lots of the things that sort of some of us grew up with. And then eventually vaccines came along, and some of those are in our past, if we're lucky. We were not familiar with COVID-19, the illness caused by SARS-CoV-2, because we were not familiar with this virus. And that's one of the things we're going to talk about next, is what that lack of familiarity meant to us as human beings. So you'll hear people talk about, oh, it's a non-envelope virus, it's an envelope virus. It's just like it sounds. An envelope virus has more layers protecting that genetic material. The more layers that are protecting the genetic material, the more likely that genetic material is to remain capable of infection. So when we're trying to get rid of SARS-CoV-2, we have to pick a way to get through all of those layers and essentially destroy the genetic material. One of the questions we continue to have about that is whether the fragments of the genetic material can also be just as destructive as the whole genetic material. And so we err on the side of caution as far as trying to get rid of as much of this in the environment as we can. Sometimes people ask, well, could we do one or the other? We can. We can wait this out. We can essentially say, oh, well, this virus isn't going to last forever because it's not going to infect something. It doesn't work that way most times, though. Most times the virus finds a way to infect something. And this is how that pattern goes. You see at the top towards the, let me see, right upper corner, as I'm looking at it, you'll see number 1. This diagram is talking about DNA. DNA is a type of nucleic acid molecule. RNA is what SARS-CoV-2 has as genetic material. They're quite similar in their structure. They all carry a code to do something. And in this case, to make more viruses. So the coronavirus would attach itself to the outside of the host cell. And then it would inject, almost like propelling the genetic material into the cell. Once in the cell, as you see in number 2, it actually becomes part of your genetic material. It makes a space for itself somewhere in your DNA or RNA, depending upon which type of nucleic acid molecule was injected. Ultimately, once it becomes part of your genetic material, it takes over this cell. And now, instead of the cell being what it was meant to be, it becomes a factory for viruses. It replicates more and more viruses until finally the cell explodes and releases those viruses into your body. The more virus that is released into your body, the more effect. And this is exactly what happens with all viruses that are pathogens. They don't essentially get into your body and set up shop and make their own home and make new viruses. They use you, a true pathogen and a true parasite. Now let's talk about our other 2 life forms. We mentioned that sometimes they're hardy enough also to live within our environments, to stick around longer than we want them to. If you look at the picture, you'll see that there's a green dot and it's surrounded by sort of a red dot on two sides. That green dot that you see is an endospore. It's the hardening of the outer casing of the bacteria, making it more likely that that bacteria will move through the air. I mentioned that molds can also form spores. Keep in mind, there's two different terms here. Endospores are bacteria, spores are from molds. Why this is important is because when we're talking about how things move through the air, those viruses, the endospores, and the spores, they're all very similar. They move through the air as what you would consider to be dry particulate matter, and they can move readily through the air. So what do? Well, we try to find chemicals that work. And a long time ago, for most of us, in 1947, the EPA, which hadn't even been made yet, so to speak, but the primordial EPA, set up an agency called FIFRA. FIFRA's onus was to deal with fungi, insecticides, herbicides, and to try to figure out what worked and how to protect people as they were using those chemicals. So since 1947, FIFRA has been generating research. And when EPA came into existence in the 70s, FIFRA talked with the EPA and they set up a particular registration protocol for the chemicals that are used against pests. All of those microorganisms we talked about can be pests. So EPA deals with those pests in the environment. FDA deals with them from a medical perspective. So in the research that we did, we turned to EPA. At first, they said, well, we know some of these things can work against viruses, but we haven't been focused on that. And so we looked back at the registration information from bacteria, from fungi, and we looked to see, did you do any research that showed this worked against an enveloped virus? You'll see the table there, and off to the left, you'll see, wow, this one hit. This particular chemical and its registration, it had been tested against a virus. And so we knew there was some hope that that chemical would work. Ultimately, EPA set up what was called List N, and List N did exactly what we had been doing, parallel to them, which is developing a list of chemicals that could work against a virus. Now we had a path. We had a way to attack what was happening in our environment. So parallel to all this, remember I said that, well, FDA deals with the medical effect, and that's not in EPA's onus. I'm not a medical doctor, but one of the things we had to also research is what's happening with the immune system. Why are we seeing a situation where this virus seems to run unchecked through the population, seems to essentially affect some people severely? What is happening in the environment that maybe we can change so this happens less often? And what are we just going to have to, partner with the medical community and figure out something together, which is, of course, what we did. So do you see a difference between the left and the right side? In your body, you have some sort of magical cells. They're called stem cells. They have the ability to make other cells. Almost, it seems like from nothing. But what's really happening is they have a lot of genetic recipes within the stem cell. And depending upon what your body needs, they can make various things. So I'm going to turn my attention to the right side here. You'll see one time the stem cell, they said, well, we need more red blood cells. And so they made the myeloid stem cell line, and that made red blood cells. Another time they said, you know what, we actually need more things to deal with our immune system. So they made lymphoid stem cells. And that ended up making two very important components. One is called a B cell lymphocyte. The other is called a T cell lymphocyte. Now, this wasn't the only thing we could use to attack the virus. It wasn't just the things that came from the lymphocyte stem cells. We were also able to, again, look at the myeloid stem cells, and they would make granulocytes, which essentially produce a type of white blood cell. So we had a means, we had a mechanism within our body. The problem was we didn't have a correct recipe. With a novel virus, the things that the T cells and the B cells and the white blood cells would identify, mainly because of the T cells recipe, there was no path. There was no way forward. We could do a little bit, but we couldn't really attack the virus in the way we could if our body had the recipe. The recipe ultimately comes either from infection or in some cases from immunization. But in this particular case, we were at a loss. It's one of the reasons we realized very early on that we were dealing with something new, at least new to the human population. So what happens? Well, the virus gets into the body and this wheel starts turning. So does the time clock. And if the virus is there long enough, it can actually deactivate the T cells. It can make them so they don't work, so they can't even develop a recipe if they want to. And the longer it takes for your body to recognize the virus, the longer it takes for your immune system to work, and maybe you develop some sort of immunity, the more likely you are to have health effect. And here is the hurricane. In addition to producing those viruses that we saw erupting from the cell, essentially becoming so populated within the cell that the cell bursts open, the cells can also release what are called cytokines. And those cytokines, once they get into your body, create a storm if there's too many of them. And instead of the immune system helping you, it starts to hurt you. These are the people that ended up in situations where they were in acute respiratory distress, pulmonary failure, cardiovascular failure, kidney, which is renal failure. It's because in essence, the body is somewhat attacking itself. And taking someone out of a cytokine storm, restoring them to health, extremely difficult because the body's working against itself and you're trying to figure out how to deal with that and still keep the body itself, of course, intact. So what did we hope for? We hoped for the very beginning that somehow the body would get the recipes, immunity would develop, and we would move towards community immunity. When that didn't happen, we realized that we had to use lots of other things to protect people, including ultimately immunizations, various drug therapies, and also changing our environments. Now, one thing I always want to point out to people is community immunity is not the same as herd immunity. Herd immunity means we let the weak go. Community immunity is moving forward to protect everyone, including the weak, with the hope that ultimately we'll have enough people immune, and not only immune, but shedding immune factors into the environment so that we'll be protected as a population. The magic number at first was 70%. Community immunity, 70%, good to go. That number sort of wobbles from time to time, but we are seeing community immunity now. And that's one of the marvelous things about the human body, that essentially we can do that and protect ourselves. And in so doing, we can protect others. So going forward, what do we need to be aware of? We have to move away from just multidisciplinary thinking. When I mentioned all of the people that came together and figured out ways to move forward with the recent pandemic, one of the marvelous things, and this happened across the globe, is we also developed what's called transdisciplinary thinking. That means essentially sort of like what's happening here today, is that all people who had a stake in making these interior environments better and ultimately using that concept in addition with the medical concepts to go forward, coming together, we found solutions much quicker. We sometimes had to learn each other's language. And that's going to be a continuing phenomena, I believe. But ultimately, the meeting of the minds is just that. It's a meeting of the minds. And it makes it possible to move light speed, which is what happened in this pandemic. Think of what we learned. Think of what we know now about viruses and viral transmission, and what we know about where we live and work. So what does a meeting of the minds involve? Well, there has to be collaboration. We have to talk to each other, sometimes at great length. It is incremental, though. You do not see the end point. When we first started this discussion at the very beginning of the pandemic, we did not see the end point. We hoped for a quick end point. And when that didn't happen, we, as I mentioned, had to reevaluate our thinking. We had to reevaluate not only how we were thinking about this pandemic, but how we would think about pandemics in the future. We had to go to guidance documents, sometimes regulations. We had to look at science, but look at science in a new way. Look at science as it regards not just its effect, but its future effect. In other words, if we're going to change how our environments are, if we're going to strategize how we live as a human population to make these types of events easier to deal with, we have to think of new things, things that have never been thought of before. This became particularly evident when it was discovered that this pathogen, SARS-CoV-2, could move through the air. Now we're no longer dealing with just, did I get too close to someone when they sneezed? You know, did I pick up an object that they'd had in their mouth? Did I touch my eyes after I touched a contaminated surface? Now we're dealing with the fact that the very air we breathe, the air in our environments, had to have different controls so that we could make things safer. So this is a splash screen showing really the I would say the dynamic part of putting all of this transdisciplinary knowledge together. You'll see on one side the different categories, things that you as designers worked with every day, always. What type of material? What are the design considerations? Are there specifications we have to follow? Are there rules that we have to follow? Maybe there are clients' rules. Maybe there are government's rules. Is there a way we can protect these surfaces so that essentially they don't degrade over time? Yeah, are there bodies out there that can give us certifications, that can run tests? And ultimately, once this has reached its life cycle for its first use, can I reuse it? And then you will see embedded through all of these considerations what you see on the right, which is, can I decontaminate the surface? Is there a way I can decontaminate it without destroying it? Is there a way I can decontaminate it so it doesn't become basically a playground for pathogens? And what does that ultimately mean? Well, it means different things depending upon what pathogen you're talking about. If we're talking about something that lives independently, we probably have a longer period of time when we have to carry out decontamination. So bacteria, fungi, longer period of time. Viruses, we thought at the beginning, they'll last maybe 3 hours. We found out later that they didn't really have to last. A piece of them could last. A fragment of that genetic material could last. And we had to have consideration for, well, maybe we have to keep decontaminating these surfaces a little bit longer than 3 hours. Maybe it's not just a situation where we go home at night and then come back to work the next day and everything's clear. And so the methodology that came forward is what you see here, at least examples of it. One is the simple wiping of surfaces, spraying of surfaces, different types of spraying, low pressure, high pressure. All of these events are wet events. Hopefully you're not wiping down things that are dry, because wiping down things that are dry, just like vacuuming, which is you see here on our chart also, it resuspends particulate. What that means is essentially the stuff that you thought stuck on the table, it's now in your airstream again. Once it's in your airstream, you don't have to touch the table to get it into your body. You just have to walk into that airstream. So we don't want to be resuspending viruses or any pathogens. Next, can we use hot water? Can we use drying? Well, bacteria, fungi, some of these things work pretty good. Viruses, especially an envelope virus, may have to do more than that. Regardless of how much we would like to have a world where we don't have to use some of these chemicals, we found out we had to use them. We had to use them essentially to get through that envelope, get through to that genetic material and destroy the infective capability of the virus. So what are biocides? Biocides are life killers. That's exactly what it means. Can they affect you as a life form? Yes, they can. They're poisons. How poisonous they are? Well, it varies. The 4 that you see here, the concentrations make all the difference. We have one, however, we have one winner in the 4 that you see here. Just take a good look at this chart. Look at the second column, the class of disinfectants. Think to yourself, I wonder which one of those is the winner. I'm going to tell you what we came up with, but you'll see that they all have various properties. The alcohols work by drying. So those viruses that don't dry out very well, the endospores, the spores that don't dry out very well, alcohol doesn't work so good on them. Have to put it in essentially a liquid suspension and keep it on a surface, including your hands, for a long period of time. At first, we thought we had to keep the alcohols on your hands for 4 minutes. Did you keep the alcohols on your hands for 4 minutes? 4 minutes in a liquid state? Later on, we had test results that show it worked quicker than that, but we had to up the percentage of alcohol. Quaternary ammonia, you may think, well, I don't know what quaternary ammonia is. I can remember I thought that at one time. Quaternary ammonia is a ubiquitous disinfectant. It is basically in most disinfectants and sanitizers and cleaning agents that you buy, a form of it. It's easy to produce. It's readily available. We need quite a bit of it to achieve the disinfection that we want. Accelerated hydrogen peroxide, you may think, oh, well, hydrogen peroxide, what's this accelerated business? I'm going to tell you in just a minute. Hydrogen peroxide works by imparting oxygen. Essentially, oxygen starts the dissolution of the outer shell of a virus. In terms of bacteria and fungi, it can actually also work as a poison, again, depending upon the percentage. Chlorines and bleach, chlorines. Chlorines and bleach work very, very well, but they also, at about 1 part per million, start to make you not feel so well either. And so the permissible exposure limit at 1 part per million means that we have to be very careful how we apply these to large surfaces so that we can protect the workers from the chlorine and from inhaling the chlorine into their lungs. So what's wrong with this picture? So I mentioned earlier that we'll talk just about viruses now. We said that alcohol acts by drying. And I told you that the envelope viruses, they have a fat layer, they have a protein layer, that's their envelope. And in order for that viral particulate to be destroyed, rendered ineffective, we have to get through all those layers. So it takes a while. It takes a while for the alcohol to make a pathway to the genetic material. If we were talking about bacteria, which is the next item you see here, we're switching now to bacteria. It's a little easier because now we're just dealing with cell walls. And cell walls have more, well, let's say holes in them, pores. The alcohol gets in, it can act as a metabolic poison inside the cell, and it also essentially causes the cell to desiccate, to shrink. Same is true for fungi. Not so true for endospores or spores, for those, bacteria that are special, or the fungi that are moving around in the spore state. So what's the problem? Well, the problem is, first of all, what's wrong with this picture? The finger that you see on the push device, contaminated? Are the dispensers decontaminated in between each use? Or is the next person touching it going to receive what the last person had on their finger? The alcohol, once it gets into the palm of your hand and you rub it on your hands, are you going to hold it there Are you going to put enough alcohol on so that you have that liquid film for at least a minute and probably 4 minutes? And last but not least, at what point is it a false sense of security? Essentially, I can do anything I want as long as I put this on my hands. Those were the questions we faced. And so now we see dispensers that don't require us doing this, pushing down on a dispensing arm. And we see people keeping this on their hands for a long period of time, singing, what was it, Mary Had a Little Lamb, for if they're washing their hands. But if they're using alcohol, it's even longer than that. Minutes, minutes, minutes. Chlorine. Sort of the standby. Will it get through those layers? Oh, yes. Does it take time? Yes. Again, 4 or 5 minutes, maybe as much as 10 minutes. And that's when we're talking about chlorine in its sort of right out of the bottle form. Right out of the bottle, it's 3 to 7% actual chlorine, available chlorine. Can we get higher percentages of chlorine? Yes, we can. But it starts to be a big issue as far as using chlorine in higher concentrations for the people who are using it, who are applying it. Can we apply it as a dry granular, like what you would throw into your swimming pool? Yes, we can. But again, we have to hit that high concentration level or a lower concentration and a longer dwell time. Can we use chlorine dioxide, which is a gas? Yes, that was used against anthrax. We pushed it into buildings through the ventilation systems. It's called a chlorine push. And essentially it gives us the opportunity to disinfect the air. But we do it in respirators, protective respirators, sometimes supplied air, depending upon what part of the building we're in. So it's not the kind of thing we're going to do on a day-to-day basis in the places we inhabit normally. Quaternary ammonia, the acronym for this is QUAT. Look at the bottom of the slide. Those look like interesting terms, but notice they have something in common. Chlorine, chlorine, chlorine. Chloride is a type of chlorine, various states of chlorine. And you can see ammonia, ammonia, ammonia. Remember when your parents told you don't ever mix ammonia and chlorine together? They're right. You don't want to do that. You don't make this yourself. But you can find it readily available. Others have made it in a controlled fashion. Does it work? Yes. Does it take a longer time, longer than straight chlorine right out of the bottle from that bottle that you bought from the grocery store? Yes, it generally takes longer. But we can apply it to large surface areas. So if we have time and opportunity for time to work in our favor, we can use this chemical. And we did. Floors are a good example. That's where it works well. And now hydrogen peroxide. Remember, there was a special term called accelerated hydrogen peroxide. That's not the hydrogen peroxide you buy at the store for wound care. It's very special. It's combined with what's called a surfactant. Surfactant is sort of it's a sticky molecular chemical that holds things to surfaces a little bit longer. And when combined with hydrogen peroxide, it held it on the surfaces. And it held it on the surfaces long enough for the hydrogen peroxide to work. And if you did your homework and you went to FIFRA and you looked up those registrations, even before this pandemic, you could find products that worked within 30 seconds. And that's exactly what they were, this special type of hydrogen peroxide. Now we see them everywhere. They've been used in the medical community. They've been used in my line of work when we're decontaminating facilities on a general basis for years. They were not at first readily available to the public. They were partitioned off for medical use. But over time, our manufacturers across the globe essentially figured this out and started making more of these products. These are the winners right here. Hydrogen peroxide combined with a surfactant. Now, can we use it everywhere? No, it's actually a mix of things that we use for decontamination and disinfection. And let me point out one more thing before we leave this slide. When we talk about disinfection, we're talking about not sterilization. We don't have that capability in a normal environment. We're talking about getting the loading of those microorganisms to a particular number, and that these chemical manufacturers have proven they can do that with these chemicals. The lesser step is sanitization. We have to move to sanitization if we're dealing with a surface where we're going to use food. So that surface you see being cleansed there, if that's a countertop in a kitchen, we probably are going to move to a sanitizer. Why? Well, because we may not want to put a chemical down that is a biocide on that surface at the concentrations that would disinfect. So instead we'll sanitize. And we look to FDA for what we can use in that regard, not just FIFRA. You know, is this something that food contact surfaces have been tested on? And for not just for efficacy, which is how well the chemical works, but for safety for human beings and their ultimate food consumption. Way down at the bottom is cleaning. Cleaning is the mechanical removal of dirt, grime, soil. And the old way was to do various types of disinfection with cleaning first. The new way in the pandemic was to do it all together. Now, in case you think you haven't seen accelerated hydrogen peroxide in the grocery store, you have. Here's two common products. There's others out there now. There's lots of others out there now. In part because this chemical, which is percarbonate, is now in lots of products, and you will see it advertised on the products. This is a very good thing that happened within our response to the pandemic, is that these products are now on the market, and they're on the market for you to use all the time. So instead of just cleaning something, you're disinfecting it. And hydrogen peroxide, this is when it's sodium percarbonate is combined with sodium, which is like salt. When it's just hydrogen peroxide, it's what you see at the top. You know what it breaks down to? Hydrogen and oxygen, hydrogen and water. So as long as there's not a bunch of other stuff mixed in it that's going to make it problematic, this is a really good disinfectant. So how did we track it? Well, we developed databases, lots of databases. And we got all of the information that we talked about, we've talked about here, and all of these columns are interlinked. Now they're being interlinked with surface types, with material selection criteria, with durability, with environmental influence. And it's a big job, but it was a necessary job for the pandemic, and it's necessary going forward as we face the future, as we make decisions for the future. Not only about what biocides to use, but what can we use these things on? Should we be using materials where we can't use these? And if we are going to use these, are those things that we're just going to have to throw away during a pandemic? Lots of decisions, lots of opportunity, as long as we stay transdisciplinary and keep talking to one another. At first, what we heard is SARS-CoV-2 does not move through the air. Most of us, especially the biologists and mechanical engineers, when we talking together, we said, no, it's a particulate. It's going to move through the air just like anything, just like dust does. The question becomes, is it going to move through the air and stay infective long enough for people to inhale it, for people to get it on their fingers and touch their eyes, which, by the way, is one of the best ways to infect yourself. Because when you touch your eyes, essentially your tear ducts go into your sinuses, and then that's behind your nose, and then you infect your respiratory tract. So what can we do to essentially not make this airstream a problem as people walk through it? Because we had a pretty good idea that this SARS-CoV-2 was capable of staying infected for a time. ASHRAE, which is an industry standard, eventually came out and said that it was sufficiently likely. Now, this didn't happen right away. This is several months into this process. But ASHRAE sort of prejudged this. And so if you think about the pandemic starting about the first of the year, maybe February, us having sort of a knowledge of it in the United States, this is coming out in April, coming up actually very quick. Again, their scientists got together and they said, it's likely enough that we need to look at reducing airborne exposures. We need to look at ventilation and filtration, and we need to make decisions that sometimes we've never made before. Now, was there a time when some companies came forward with things that maybe they wanted to work, but they didn't work? There was. And so just in the way that we looked at biocides, we went back to the science. What can you prove to us? What can you prove to us about how you're controlling the airstream, about how your filters work, about how your devices work? We couldn't go to FIFRA because they don't register devices in the same way as they do pesticides. So we had to go broader. Huge transdisciplinary effort to try to figure this one out. So what's the reality? The reality is that oftentimes your air is being transmitted through dirty systems. And I don't mean just a little dirty. And all of those layers of dirt and contamination can essentially harbor pathogens. Now, that wasn't quite the same issue for viruses as it would be for bacteria or fungi that can start living there on their own, but it still is an issue. So we've got a dirty system. How do we decontaminate it? Will filters work? Are filters all that we need? Is there something else that we can do as far as using chemicals? Can we use energy? I will tell you, this has not been solved. We are still in the process of figuring out this part of the equation. But what we do know is if you select the right materials, if you select the right interiors, the right furnishings, and then you also are lucky enough to have really good HVAC designers, we could keep that environment cleaner, for sure. And when we need to, we can actually move to disinfection. But this is our challenge moving forward. How do we put all these pieces together? How do we make our facilities what they need to be in the future? Now, I just started traveling again for work, and so I've been in airports quite a bit. I've seen huge changes. I've seen huge changes, not just in material selection, but in touchless features, in how people address various portions of the airport as far as how they queue up. All to the good. I hope it continues. I hope all of this continues. And although I hope I never see something like SARS-CoV-2 again, all of these other things that are pathogens in our environment and always have been pathogens, we'll be addressing those too, hopefully before they ever get to pandemic form. So the future is ours, as long as we keep talking.